Okay, so the that scheme of Eratosthenes, the scheme of Eratosthenes allows us to calculate all the prime numbers less than some given integer. And that fact itself raises one question whether there are infinitely many primes or only finitely many primes are there, and of course we all know that there are infinitely many primes. And the proof of this fact was given by Euclid in book 9 of his Elements, and that proof is regarded as a kind of standard of mathematical beauty. So let's see the proof. You may already know this. The proof is by contradiction. We want to prove that there are infinitely many prime numbers. So we assume the opposite. Suppose there are only finitely many primes. Suppose only finitely many primes exist, and let them be these for some positive integer n. We don't know what n is, but there is, according to our supposition, there is a positive integer n, and such that there are only n prime numbers. Okay. Now consider the integer capital N, which is the product of all these prime numbers plus 1. Since n is greater than 1, n is greater than 1, we can see that, of course, and in fact that's why we have taken plus 1, but there is another reason also, which will become apparent when the proof is over. Since n is greater than 1, the fundamental theorem of arithmetic ensures that there is a prime number say q that divides n. Any integer greater than 1 has at least one prime divisor. But now note the consequence of our supposition. Because we have supposed that these are the only primes, so q must be one of these, since the only primes are our qi's we must have q equal to qi for some I. For some I in this range, of course, between 1 and n, including 1 and n. It may be 1, it may be n. But then but then something happens which gives us an absurd result. Okay. But then, let me write it here. Q divides this product. Why? Because Q is one of the Qi's. Q is equal to Qi for some I, so naturally Q would divide this product. And so, Q has to also divide, because besides dividing this product, Q also divides N, and that is why Q has to divide this difference as well. However, this difference is nothing but 1. And this is not possible because no prime number divides 1. We already know this. That is why our supposition must be wrong. That is, there cannot be finitely many primes. There has to be infinitely many primes. So that is just the proof. I mean, you can write that last line and that's just it. So the proof is really very elegant, and it also establishes a result which is not trivial. I mean, proving that something is a class of numbers is infinite, okay, that too the proof is not extremely difficult, so that's why it's elegant. Now the numbers that appear in this proof, that is numbers which look like this, because they appear in this proof, they are also called, I mean, they might be called, according to the author, I don't know if this is a standard term or not, Euclidean numbers. So if we are given, say, a prime number p, then we can have this notation, okay, we can denote by p hash the Euclidean number, which is the product of all the prime numbers less than or equal to p plus 1. Well, in this text, by p hash, actually the author is not denoting a Euclidean number itself, but the product of all primes up to p. Okay, all primes less than or equal to p, so that means we have to add 1 to it. Anyway, so let this be the product of all the primes less than or equal to p. Then this is a Euclidean number. Now the thing is that the first few Euclidean numbers are prime, but then composites also appear. For example, if one looks at this first few numbers, 2 hash plus 1, all the prime numbers less than or equal to 2, there is only one such number, which is 2 itself, and 2 plus 1 is 3. This is the prime. Then 3 hash plus 1, here the prime numbers will be 2 and 3, and 2 times 3 is 6, 6 plus 1 is 7, that is also a prime. Then 5 hash plus 1 will be what? 6 times 5 is 30, 30 plus 1, 31, that is also a prime. And then we have 7 hash plus 1, which turns out to be 211, that is also a prime. And then there is 11 hash plus 1, which is 2311, that is also a prime. But if one becomes hopeful that this is always going to be the case, then one will be disappointed, because composites soon arise in this list. For example, it turns out that 13 hash plus 1 is this composite number, 59 times 509. Then 17 hash plus 1 has this factorization, 19 times 29 times 97 times 277. Then 19 hash plus 1 is also composite, and here there is this factorization, 347 times 27,953. If you want, you can verify these things, okay, because factorizations are given for these numbers, so it's not really difficult to verify that they indeed are these numbers. See, multiplying two numbers is not a very big deal, but factorizing a given number into its as a product of its factors, that is really difficult. Now, it is not known whether there are infinitely many Euclidean numbers which are prime numbers, and the only prime numbers that are known so far means there may have been an increase in this list. I don't know what is the current state of Euclidean numbers being primes, but the author says that 18 primes of the Euclidean number form have so far been found, and these are these numbers for these values of p. The first few we see here. So when p is 2, 3, 5, 7 or 11, then of course these corresponding Euclidean numbers are primes, but here we have these other values also, 31. The next few, the three are not prime. Okay, they turn out to be composite, but then again primes appear. 31, 379. It goes quite far. Then 1090. These are all primes. Okay, for them the corresponding Euclidean numbers also turn out to be prime. Then 1021, 2657, 3229, 4547, then 4787, then and then it becomes really big. I mean, the primes themselves are getting big, so the corresponding Euclidean numbers will be even bigger. 11,549, then 13,649, then 18,523, then 23,801, and there is another one. For this last prime that now I am going to write, the author gives us an idea of how big the corresponding Euclidean number is. And the last prime here in this list is 24,029. For this value of p, the corresponding Euclidean number has 10,395 digits. For this p has digits, and it was discovered in 1995. And it has also been found that the Euclidean number p hash plus 1 is composite for all other p less than or equal to this quite large number 35,000. So all the primes less than or equal to 35,000 have already been checked, and among them it has been found that these are only the 18 instances in which the Euclidean number becomes prime, and in all the other instances they are composite. Okay, but still that question persists whether there are infinitely many Euclidean primes or not, or for that matter whether there are infinitely many Euclidean composites. Okay, so that is still there, and I think it's still there, I mean now also. And now there is an alternative proof of Euclid's theorem itself, that is of infinitude of primes. Let's see that also. What the alternative proof does, it gives us a sequence, a recursively defined sequence. The sequence starts with n1, which is 2. Okay. Actually, it does not matter what we take as n1, because the proof depends not on the actual terms of the sequence, but rather on something else. Then n2 is n1 plus 1, then n3 is defined to be n1 n2 plus 1. So you can see that it, in a way, it mimics the original Euclid's proof, in that here also we are considering numbers like p hash plus 1. The only thing is that now we are not considering primes or anything. Okay. Then let us write one more term, n4, or maybe two more. n4 is n1 n2 n3 plus 1. n5 is n1 n2 n3 n4 plus 1, and so on. So this is how the sequence goes. Now you can in fact start here not with 2 but maybe with 3 or something else. It needs to be greater than 1. Okay. Now the point here is that each ni is greater than 1, right? So by the fundamental theorem of algebra, each ni is divisible by some prime p. Okay. Now the next thing we note here is that distinct ni's are relatively prime, that is their GCD is 1. Let us see why. Suppose you consider two distinct indices, positive indices of course, say I and k, and suppose I is less than k. Then what about the number nk? Then you know that nk will look like this, n1, n2. At some stage there you will encounter ni, okay, n k minus 1 plus 1. Why is that so? That is simply because I is less than k. Now if you bring this term on that side, then you have n1, n2. So if I want to write that I mean after writing all the other factors, then I would write like this, nk, and then I write ni, but of course I cannot write simply ni, I have to write minus ni. So let me introduce that minus sign with this one itself, minus of this times ni plus 1 times nk is equal to 1. Okay. Then you know that whenever you have two integers and you find two other integers and 1 such that such a combination is 1, then the GCD of these two integers is 1. That is, the greatest common divisor of ni and nk is 1. If you still need a reason for why exactly that is true, you just consider a common positive divisor, say d divides ni and d also divides nk. D is a common positive divisor of ni and nk. Then you use this equation, because d divides ni and d also divides nk, so d would divide this integer combination of ni and nk where the coefficients are integers, and as a result d also has to divide 1. That means 1 is the only positive common divisor of ni and nk, and that is why that is also the greatest common divisor. That's how we are getting this. So it means what? All of these things ultimately imply what? they imply that fine, each ni is having one prime divisor, but due to this fact that they are mutually relatively prime, they cannot have common prime divisor, because if that is the case, then that common prime divisor has to also divide their GCD, because it's a common divisor, and then that has to divide 1, but no prime divides 1. So that is why these ni's would have distinct prime divisors. But the ni's themselves are distinct, and there are infinitely many of them, and each one of them has a prime divisor, and the prime divisors also need to be distinct. So that means that there should be at least as many prime divisors of ni as many ni's we have, namely infinitely many, and that tells you that there are infinitely many prime numbers. Okay, so this is another way of getting the infinitude of prime numbers, and the proof is somewhat like Euclid's. See, this is not as elegant as Euclid's proof, but it mimics Euclid's proof. The only thing it does is that it avoids primes in the beginning, but then primes appear because of the fundamental theorem of arithmetic. Okay, so this is another proof. Now we go in another direction. Suppose Pn denotes, let Pn denote the nth prime number when the prime numbers are arranged in their natural sequence. Natural sequence means that sequence where the smallest prime appears first and then the next smallest one appears, like your natural sequence of primes 2, 3, 5, 7, 11, 13, that thing. In that sequence, say the nth prime is being denoted by Pn, which means that P1 is 2, P2 is 3, P3 is 5, P4 is 7, P5 is 11, and so on. In their I should not write natural sequence, but natural order, yes. And that order gives us the natural sequence, and that's how we get the nth prime number. Okay, now notice one thing. Suppose we consider say we consider this Euclidean number Pn hash plus 1, which means what? It is P1, P2, P3 like that up to Pn plus 1. By the fundamental theorem of arithmetic, this number, because it's greater than 1, it must have a prime divisor of its own, at least one prime divisor. Now, what can we say about that prime divisor? We of course cannot know what that prime divisor is, I mean not so easily or in general like this, but it is there. It is something which divides this. But we can still say something from simply this situation. What is that? You see, can this P be any one of these Pi's? Of course not, because if that had that been the case, we would have again obtained that absurd result that p divides 1, because p is already dividing this. Now if p happens to be here itself, then p would divide this product, and that's why p would then also have to divide 1, which is not possible. So that means this p is none of these primes. However, these are all the primes up to n, up to the nth prime, which means that p has to be greater than all of them. Actually, because they have been arranged in their natural order, so the other primes, as we write from this side, they decrease. Okay, and eventually we reach p1, which is equal to 2. And this p is greater than them, simply because it's not equal to any one of them, and they are the first n primes. But what about Pn plus 1? Pn plus 1 is the prime that appears right after Pn, that is the next prime. And so that means, in other words, Pn plus 1 is the smallest prime greater than Pn. However, P is some prime greater than Pn. So the smallest nature of Pn plus 1 would imply what? That Pn plus 1 has to be less than or equal to P. It may be P, but it may be less than P also. Alright. So what does that tell us? It tells us that, okay, see, you now notice another thing. P is dividing this number, so definitely P has to be less than or equal to this number. P cannot be greater than this number, right? From properties of divisibility. So you have this. Now you combine this with this inequality, and you are obtaining this. In other words, we are obtaining this inequality. This nice looking inequality okay, where n of course is a positive integer, so it's greater than or equal to 1. Now this may look like a very nice result, okay, that we have obtained just from this simple argument. Unfortunately, it as nice as it looks, it's not very useful. You see, what it does is that it tells us about the maximum possible size of the prime Pn plus 1 in terms of the previous primes. The unfortunate thing is that the actual size of Pn plus 1 in practice is really very small compared to this number. So it really does not give, it just gives us a very crude upper bound. It does not really tell us how small this is. That's because this itself is already very large. If one goes through a similar argument by tweaking some things a little bit, one gets this slightly better inequality. Well, but before that, this itself can be written a little differently, like this: Pn less than or equal to P1, P2, etc. plus 1. The only thing is that now you have to start your n with 2, n from 2. Now this inequality can be slightly improved to this. Instead of plus 1, you can consider minus 1. And here your n has to start from 3. Now to give you an idea of how bad it actually is, say you consider the case n equal to 5. So we know what P5 is. P5 is the 5th prime. 2, 3, 5, 7, 11. So that means P5 is 11. And that should be less than or equal to, according to this inequality, P1, P2, P3, P4 minus 1, or 2, 3, 5, 7 minus 1, and this turns out to be equal to 209. Is it really 200? I haven't really checked these things. Okay, I have simply copied from the text. Let me see. Yes, it's 209. So you can see clearly that it is really not telling us, it just simply tells us that P5 is not greater than 209. But the actual size of P5, which is 11, is in fact much smaller than 209. So it's a very bad upper bound, but an upper bound nonetheless. Now this can be improved. And you can have something called Bonds' inequality. This part is more like some pieces of information. That is, the author is giving us an idea of what is out there, not really going into details of these things, but just a rough idea of what the things are. And all these things are related to prime numbers, nth prime, distribution of prime numbers in several different ways. And Bonds' inequality tells us this, that the square of the nth prime is less than or equal to the product of the previous primes, where n is at least 5. Why is this an improvement of this inequality? That's because now, see, unlike this thing that just says that Pn is less than or equal to this product minus 1, this one says that Pn is less than or equal to the square root of that product. Okay, which is smaller than this upper bound. Now, what do we get from Bonds' inequality in the case n equal to 5? In this case, we have P5, which is 11, less than or equal to this. So that is the square root of 210, which turns out to be 14 point something. 14 point, I have it here, I think, yes, 491, something like that. So you can see that already the upper bound has come down significantly. Previously it was 209, now it is 14 point, which is much closer to 11. But still there is another slightly more improved inequality, and that inequality is this: P2n less than or equal to, okay, this one on the other hand starts with P2. See, we won't know why the inequalities look like this unless we see their actual proofs, which is not present here. Minus 2, and here n is greater than or equal to 3. Why is this one even an improvement of this one? That's because you see here we are not really saying how large Pn is, but rather how large P2n is. Now P2n of course is larger than Pn, and in finding this upper bound for P2n, we actually do not have to go all the way up to P2n minus 1. We are only using these primes. So that's why this is an improvement. However, let's see what happens in the case n equal to 5. We cannot of course have P5 here because it needs to be even. But we have P5 less than P6, and P6 is 2 times 3. So that, according to this inequality, should be P2 times P3. And you see that we can use this inequality because 2 times 3 we have here, and 3 is the smallest value that n can take, minus 2. So what is P2? The second prime, that is 3 times the next prime 5. 15 minus 2, that is 13. So this is the smallest upper bound that we have obtained so far using these inequalities. So yes, it is an improvement. Now the problem with these upper bounds is that they all need a knowledge of the previous primes. However, there is an upper bound which depends only on n, which is our next result. But because of that dependence, it's going to be an extremely bad upper bound, something like this one. No, actually it's much worse than all of these things. The only advantage is that it depends only on n, and it does not require a knowledge of the previous primes. So this is theorem 3.5. So it just simply states this: the nth prime is less. Is there equality? Yeah, there is. There is one case in that case you have equality. You see, this is already quite big. 2 to the power n minus 1. Now the proof of this is by induction. Oh, I wanted to write solution. This has become a habit. The proof is by induction on n. So let's just go through the steps. When n is 1, you can take n equal to 1. Then you have P1, which is what? 2. On the other hand, what do you get when you put n equal to 1 here? 2 to the power 0 as an exponent. That means the exponent here is 1. And 2 to the power 1 is 2. So this is the case where you have equality. So that means this can be the this can be the stage where things start. It is the basis of our induction. Next, you assume induction hypothesis, which is just this. So for some positive integer n, you assume that this inequality is true. Okay. Now you consider p n plus 1, and here we are going to use one of these previous inequalities, because otherwise what can we do? There is already an upper bound for Pn plus 1, and that upper bound is just this one, which originally comes from that considering P hash plus 1, that thing, Pn hash plus 1. This one. Okay, this is something we already know, which is true for any positive integer n. And now we are going to apply the induction hypothesis. And here, just now I have noticed that the induction hypothesis, it's not enough to just simply assume it for some n, but rather we use the strong version of induction. That is, we assume that this inequality is true for all positive integers I less than or equal to n, where n is some positive integer, so that we can apply the inequality to all these pi's. And if you do that, you will get these things. P1 is less than or equal to 2 to the power 2 to the power 1 minus 1. We haven't written it in that form, but you can understand. This one is 2 to the power 2 to the power 1 minus 1. This is 2 to the power 2 to the power 2 minus 1, and so on up to 2 to the power 2 to the power n minus 1 plus 1. Now if you apply the usual rule of exponents, then you get this. Now this exponent is a geometric series whose sum we already know. It is this. The sum is 2 to the power n minus 1 plus 1. But of course, 2 to the power 2 to the power n minus 1 itself is greater than or equal to 1. So if we replace this one with this, then we will have further this inequality. That is 2 times this, which is equal to this. Or if you still want to write it properly, then it becomes this. In other words, we have shown that Pn plus 1 is less than or equal to 2 to the power 2 to the power n plus 1 minus 1. That is just like this one, only with n plus 1 in place of n. So this completes the induction, and hence we have our upper bound, which you can see is naturally, due to the nature of this number, is going to be a very big upper bound and hence pretty useless. The only advantage is that it depends only on n and not on the knowledge of the previous primes. It gives us a very rough idea of how large Pn can be. And there is this corollary also. The corollary is this: for any positive integer n, there are at least n plus 1 primes less than 2 to the power n. And you can almost immediately see why this corollary is true. That's because you already have this, no? For any positive integer n. By the way, why are we writing strict inequality here, although we have proved this ordinary inequality here? That's because it's not very difficult to see that equality occurs only in the case n equal to 1. And what do we have when n is 1? Here you have p1. However, here you are never going to have p1. Why? Because the smallest value of n now is 1. So the smallest thing you can have here is p2. And for p2, p3, p4 and all the other primes, you have strict inequality. Okay. So here you have strict inequality, and the other smaller primes of course are less than pn plus 1, starting from p1. You see, p1 actually has nothing to do with this. Okay, that p1 case occurs here, but p1 as a prime is less than pn plus 1. And so how many primes are we getting less than this number? N plus 1, and these are the primes at least. Okay, there may be others also, who knows, because this is quite a large number. So maybe pn plus 2 also turns out to be less than this. That may or may not happen, but we are sure of this fact at least, that these primes will be less than this number, and that's how we end up having at least n plus 1 primes less than this. There have been improvements of these bounds significantly. One idea was given by, idea means it was a conjecture by Bertrand Russell. What he said that for in 1845, long ago, he said that for any integer n greater than or equal to 2, there exists at least one prime p between n and 2n. He himself was not able to prove this conjecture though. That's why we are saying conjecture. At the time he proposed it, it was only a guess, and hence it was a conjecture. So although he was not able to prove it himself, but he did verify the conjecture to be true for all n. Man, this is really big. How much is this? 3 million? Yeah, that itself is a very big feat. So he verified it for all n less than or equal to 3 million. But it eventually was proved by the Russian mathematician P.L. Chebyshev in 1852. And it's not a very simple, let me just tell you that although we haven't said anything about how to prove these other bounds that we have seen so far, which involve the knowledge of the previous primes, those things. Okay, this one of course we proved, but in its proof also we took the help of that first bound, which uses Pn hash plus 1. But that Pn hash plus 1, that bound itself can of course be proved, although we haven't talked anything about how to prove them. but this one is much harder than proving those other bounds. Okay, but Chebyshev managed to prove it in 1852. Now, using this fact, one can significantly improve all these bounds. You see, what we have just now seen is this: Pn is less than or equal to this. No. This is what we have just now proved, and the proof is quite elementary. But using Bertrand-Russell's result, one can prove this much stronger bound, which means that this upper bound is a vast improvement over this very big upper bound, because it has been reduced. 2 to the power n for all n greater than or equal to 2. And this also can be proved by induction. In fact, the author himself has proved it. I mean, given the proof in the text. So the induction starts with n equal to 2. So what is P2? P2 is the second prime, that is 3. Is it less than 2 square? Yes, because 2 square is 4. So this is the basis for our induction. And then you assume your induction hypothesis, namely that this inequality is true for some integer n greater than or equal to 2. Okay, whether we will need the stronger version of induction, we will see afterwards. Okay. Now what happens? Now the thing is that we can use Russell's result and have this inequality. Exactly how is this coming? Okay, where is it coming from? You see, we know from Russell's result that there must be at least one prime p satisfying these inequalities. It must lie between Pn and 2Pn. That's because the n that you have here, any integer, you can take Pn itself a prime in particular. So between a prime and its double also there should be a prime in this sense. Now, if it happens that Pn plus 1 is great, if it exceeds 2 times Pn, then can there be any prime p in this region? Of course not. Why not? Because you see, the smallest prime greater than Pn is Pn plus 1 according to the order in which they are arranged. So if that Pn plus 1 itself exceeds 2 Pn, then there is no chance for any higher primes to be less than 2 Pn, because they also would be forced to exceed 2 Pn. So that is why this cannot be. That means Pn plus 1 must be less than or equal to 2 Pn, but of course it cannot be equal to 2 Pn because it's a prime. This one, however, is a composite. So that's why strictly less than 2 Pn. But now from this one, what are we going to get? Let's see. Oh yes, you see, P is less than 2 Pn. Now, you look at this, P is less than 2Pn, or we can use this itself. Now, why am I going back to that? Pn plus 1 is less than 2Pn. However, Pn itself is less than 2 to the power n. So that means this is less than this, which is equal to 2 to the power n plus 1. So that is our induction step. So that's it. That completes the induction and proves this much more efficient upper bound, much nicer upper bound, which is much smaller than the previous wild one, 2 to the power 2 to the power n minus 1. And we have also in fact obtained something else in the course of proving this, namely this one, that the n plus 1th prime is actually simply less than the double of the previous prime. Well, this needs this of course also becomes an upper bound for Pn plus 1, but it needs the knowledge of Pn itself. However, just imagine this one and that first one, which involves P1, P2, P3 all the way up to Pn. Naturally, that upper bound is much larger than this one. So this itself is also an improvement. But all of these drastic improvements have been made possible because of Russell's result. We should not forget that. Okay, it's a significant result, and that's why it's not very easy to establish also. Russell himself was not able to do it, but Chebyshev did it anyway. And finally, this section talks about numbers which are called repunites. It's a word which has been concocted from these two words, repeated units. Repunites are numbers which are written as a string of ones in when they are written as decimal numbers. For example, 11, 111, 1111 and so on. Repeated units, that's why repunites. And you can see that the number, if you play with them a little bit, you will see that besides being just like this, they look like this. This one, for example, would be, you can understand this. This one will be 10 to the power 4 minus 1 divided by 9, and these exponents are the number of ones or number of units that appear in these integers, in these repunites. So the nth repunite number is denoted by Rn, and it has n ones, and expressed slightly differently, it is just this. Now the thing that is somewhat striking or not striking, I don't really know how the number theorists view it, is the scarcity of prime numbers among the repunite numbers. There are very few repunite numbers which are prime, and this line of thinking we also had it when we were considering Euclidean numbers. That is, which Euclidean numbers are prime numbers, which are not. Like that, we can also think which repunites are primes, which are not. The scarcity is really too much. These are the only repunite primes that have so far been identified. And again, I am repeating this that these lists may already have been made somewhat larger by now, okay, because it's not a very new book, right? This elementary number theory has been around for quite some time now. So maybe these lists have been enlarged. I don't know. You can look up and see what the current state of these things are. But as the author is saying, these are the only refinite primes known so far. R2, R19, I should not miss any either, R23, R317 and R1031. A little inspection would tell you that perhaps these are primes, these indices, and yes, these are primes. And in fact, it can be proved that for a refinite itself to be a prime number, it's necessary that the indices be prime. That is, if Rn is prime, then n must be prime. This narrows down the search for refinite primes to those Rn where n is prime. However, unfortunately, this condition is not sufficient. It's not sufficient for Rn to, that you have a prime in place of n, and that itself would make Rn a prime. No, that is not necessary. And it's because of this. R5, for example, excuse me, 5 is a prime, but this refinite is not a prime. It turns out that it is equal to 41 times 271. And there is another example also, R7, 7 ones, you understand that, and it has this factorization. And also, it is, of course, because so far, according to the author, these are the only refinite primes. So one can ask a similar question here also, just like we asked in case of Euclidean numbers. Are there infinitely many refinite primes, or they are only finite in number? That question can be asked. Oh, we need not go this far in search for composite refinites. No? This itself is composite, R3. 3 is prime, but 111 is divisible by 3. 3 times what will it be? 3 times 37. So that's why this itself tells us that it's not sufficient for the index to be prime in order for the refinite to be prime. And this is how, with these few things, the section ends. And after this, we are going to, of course, solve the exercises. And tomorrow, we will solve again algebra problems from Lee's algebra in the community section. So that's just it. So see you tomorrow in the community section. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.